We'll start momentarily. We just got a flood of people entering the room, so we're letting them in.
Someone needs to invent the virtual donut and hors d'oeuvres. So when you guys start holding these, there is a little table.
Yes, please.
I guess we will soon have it with Facebook going to the metaverse, right?
Hey, I stopped getting the dings, so perhaps we could get started and we'll continue to let people in as they arrive. Is that okay?
Yep, works for us.
Okay, so welcome to our NEXUS talk, which Leonora and I are trying to reinvigorate. So welcome back, and thanks to Utica College and the Provost Office for their support. Today we're talking about the interplanetary internet communications in the new space age. And I'm going to hand this over to one of our special guests invited by Professor Ronnie. We have Oscar.
Hello, thank you to Utica College and thank you to the Nexus Talks program, Leonora and Elizabeth, who have worked very hard to make this move forward. I appreciate, and from the group, we appreciate that very much. And to Professor Ronnie Bull, Dr. Ronnie Bull, who is part of the Interplanetary Networking Special Interest Group, IPNC. We are going to hear this short acronym, IPNC, several times today, so so you get used to that. We have today, I am Oscar Garcia. I am the working group lead of the Interplanetary Networking Special Interest Group, the pilot project working group. So we are the group that develops and tests in some way this technology. The technology for the space has been developed over the years, for many years, and we have some speakers from our group that I would like to introduce, that are Dr. Ronnie Bull from Utica College, professor of information technology. We have Dr. Alberto Montilla, who is an expert in all that is space communications. Myself, that I already introduced myself. And we also have Samo Grassic from Sweden. Samo is also a doctor, a PhD from, and he has been working for quite a time or a long time in the development of these technologies and testing these technologies of communication in very challenging situations like the Arctic with snow, with ice, and where he's going to tell us many things about this. Please, next slide. The IPNC has like a goal, like the first vision, to expand the networking, the technology of communications, to interplanetary space for the benefit of humanity. Next slide. To create this vision, we have to establish the communication and the relationship with different stakeholders that allow all to work together. And our goal is also shape an interplanetary network that would turn into an interplanetary internet by developing a narrative and a roadmap on how we can do that. And we also, besides talking, we have to make this technology work. So we are all working in the promoting and increasing that the DTN, and why is DTN, and that is an important point. The DTN technology can be used also in terrestrial and space application at the same time. What is DTN? And this is an important concept. When you are in the, for example, like we are now in Earth, the situation is that you are connected directly. I am connected with you, and you are connected with all others, and at the same time you are receiving perhaps messages in your phone or emails and all that, and all happens more or less in real time. But when you are in space or in very challenging situations, the problem is that this connection is not permanent. It can be disrupted, it can be stopped. And this is what DTN means, that is delay and disruption tolerant networking. So it's a technology for communications, and my colleagues are going to explain this in deep in the next moments. It's a technology that allows to keep the communication even if the connection is interrupted. Next, please. The IPNC, the technology started around 1997 in the GPL, in Jet Propulsion Laboratory in California, with the people from NASA and from members of the IPNC board. And the IPNC as an organization that is not a government organization, it's a civil organization and distributed globally, started in 2002. So it has next to 20 years of evolution. Next. So we have a global participation of around 800 members, a bit more. As you can see, they are distributed in all the continents, North America, South America, Africa, our states, Asia Pacific, Europe, Middle East. And it's important to be aware that this is a global project. As I said before, we are talking about all the humanity, not only certain countries. We want, we think, we talk more about this, that these technologies should be available to everybody in some way or the other, as the internet is nowadays. Please go on. Next. Well, this is the board of the IPNC. The chair is from the Yosuke Kaneko, is from the Japanese Space Agency. Vinton Cerf, he's a board member. Vinton Cerf is known as one of the fathers of the internet. He was one of the first persons that, with Bob Camp, developed the technology that we are using just now in this moment to communicate with between us. Scott Burley, Scott was the developer of the ION protocol, that is one of the implementations of this technology, DTN. Well, Mike Snell is our secretary, and he is always all the time working with us, and he has been president of the IPNC. Scott is in the organization, the CCAPS, that connects all the space agencies, the different space agencies, and they try to, they work on that, on establishing common communication protocols between the different agencies. Well, Oscar Garcia and myself, and Alberto, you are going to listen to him I introduced him already. The IPNC from one of the groups, the working groups, developed the strategy toward a solar system internet for humanity, and this is the first roadmap that we are working nowadays, and also talking with the space agencies, the companies, and all that. Please, next slide. Why we need an interplanetary internet? This is a question. People say, well, but why you do this? Well, human expansion to space is an endeavor of all humanity, and it has emerged again in the last years. It disappeared for some years, but nowadays the oldies like myself have seen, for example, Mr. Shatner, that it was our Captain Kirk fly to space and at 90 years old. So we are all happy because I'm sure we can also fly sooner or later. We are not so old for that. Human life is, I think that sooner than later is going to happen to in other planets, different than Earth. And well, what is going to happen? Well, we are going to want to be connected. If you if you're going to live on another planet, or your daughter or your son goes to live in another planet, and you cannot really, it's not science fiction. It could happen, and it could happen in not so many years. Well, we are going to want to send pictures, and we are going to want to send a message, an instant message in our phones. So, well, that's what we are doing. We are trying and working to make this connection that, as you all can imagine, is not anything. But that's what we're working into, and we like this challenge. Next, please. As a concept of background, the space agencies and companies have been working and are working hard in this development for many years. The IPNC, as I told you, you can imagine that persons that have been involved in this are very interested in this happening. So IPNC is a contribution from the society and from experts into this endeavor, and we are also in touch with this organization, the space agency, the governments, and all that, to try to make this happen. But this technology has to be reliable and working, operational, so, and usable by people. What happened is that raw technology is not easy to use. We are using nowadays, or in this moment, this kind of communication because it is with a lot of software and technology above that is wrapping and allowing this to make this easy to use. Well, that's one of our goals. The members of IPNC have been developing, and we are trying, we are doing our effort to contribute to these technologies to allow space communications and also to be usable on Earth and space connected. Please go on. Next slide. A short brief for those that are technical, listening to this talk, may be interested. I'm not going to be going deep on this very much, but we have connected DTN between cloud systems like the cloud services that you all know, as there are several implementations of the DTN technologies. We are trying to make these implementations talk between each other. And also what is called routing, that is how the information moves between one connection, one node we call, and the other. And this is called routing. Of course, security is also very important, and we work on that. This is the next point, is very technical. This interfacing with programming languages, so applications can be developed when you, for example, you download an app in your phone, you are using an application. What if you are going to be in Mars, you are going to want to download an application, and this application would need to be working with DTN. Well, we're working on that. We are setting up a global testing plan. We are working with Dr. Bull in these past months on this. We have made experiments with satellites from the European Space Agency, and we're working in the ideas on other projects in this area with different implementations, and also with artificial intelligence from Google. There are applications specifically that we are developing, like medical record for space exploration. I'm going to talk a bit about that. The DTM manager that allows to manage this routine thing, that is one of Alberto's project and his company. Also a first responder system with drones and DTN. And Samo Grassic is going to talk about this technology to follow reindeers in the Arctic, but that can be applied to several other objectives and goals. Next slide, please. One of the projects, and I'm going to talk about this project because this is what I've been working for 20 years, that is medical records. It's very specific, but it is interesting in terms of that health information is important for everyone, for everybody, for all persons. So I've been working for 20 years in medical records. We have a company and a system that connects. We have several thousand, around 60,000 patients and 500 doctors and connecting and all that. So one of the topics that I started developing, and it was presented last year in YC, that is a conference about space communications, is medical record for space exploration. And we consider, and I consider that it is a use case important because person understand this right away. Next slide, please. Well, this is on the left side. You have the healthcare system of your doctor, your healthcare insurance organization, the laboratories where you go to get clinical tests, and even an app where. But if you, for example, travel to space, and now we are talking about tourism to space, we develop a technology that connects your medical record and space, and in the middle, what we call the Earth Unified Medical Records Gateway, that transforms the information on Earth at the way of the information, how that connects to space. And what we did, please, next slide. In the space, we developed a system more adapted. The screen you are seeing now is in a screen like an old screen, because most of the those who have used computers many years ago, perhaps the IBM PC or other computers, are used to this kind of screen. What happened is that many of the spacecraft, because of what is called the payload, the amount of weight that can be transferred to space cannot be so big. So we develop a technology very restricted, but does the same job as the technology in Earth. Please, next slide. So what we did, we did a consultation for a doctor in space to a doctor in Earth. In my case, I did with my medical record and with my doctor. The captain of the spacecraft make a consultation because the patient is dizzy and needs to make a consultation to the doctor in Earth, and has this form, next slide, and fills up this form. And you see what happens here. The medical record travel from space up to Earth, down to Earth, and then to the computer of the doctor. And we did this testing. And the doctor, next slide, can see the consultation in his own computer with the same system that he uses all the time. So what does the doctor do? Well, you have this treatment, you have to take that pills, or you have to take that medicine, or you have to make that exercise. So he resolves the consultation, gives a diagnosis and a treatment, next slide. And what happens? The information goes back to space. So through the gateway, this medical record gateway, transfer from his computer back to space. And next slide. In a space, the captain or the patient can see the response from the doctor. So, and can, well, this consultation, you know how consultations and patients, they go back and forth, and one asks again and the other, but this is the system operationally, and I think that everybody can understand what we're talking about. Next slide. So, what we see with this, or we try to demonstrate with this a specific topic, that is medical records, can be applied to many other situations and projects. What is important is that this technology not only can be applied to space, but also can be applied to situations where communications are not stable. For example, communities, we have very bad communications, native nations, where the communication, or situations of emergency where the communications is lost because of the antennas fall, a hurricane, or all that kind of things. Samo is going to talk more about this. And for closing this idea, the near future offers opportunities, and space offers opportunities of a new frontier that will allow exploration, discoveries, and business. And the development of these new technologies is open to entrepreneurs, to educators, to researchers, to investors. And we would like to hear your ideas. We have our contact form there. And if you would like to give some ideas, some concept, we will all be happy to answer and exchange on this project. Well, that's from my part. Our next speaker is Samo Grassic. Samo Grassic is part of our web working group. I said I did that, set his picture in the middle of the ice, very cold and smiling, and he loves to do that. So he's going to talk about ETN technology applied in the Arctic. So that's from my side. Thank you very much.
Thank you, Oscar. I hope you can hear me well. I would first like to thank Utica College and especially Ronnie Bull for inviting us to this talk. And I will present a bit the work that we've done with local Sami reindeer herder community up in northern Sweden. So next slide. So I would first like to present a bit the context of why we're using DTN and not some other kind of a technology, and as well contextualize where we are and what we're actually doing. So as we see, like, I mean, on the bottom right corner, you see the small picture or small photo of a map of Sweden, and you see we're actually located, or our network is deployed in this yellow area, and this particular area that's marked with the small red circle, that's actually an area that lacks any kind of mobile network connectivity. It is worth to say that this area is actually rather large. It's kind of around 200 by 200 kilometers approximately, and you get mobile internet coverage only on the edges of this. It's communication. I mean, the reason why, I mean, although it's like the Nordic countries are quite well known for adapting quick adaptation of modern mobile networks, this area is actually lacks any kind of communication, mainly due to the strict national policies that prohibits any permanent installations, and even more inaccessible mountain terrain where we have really high mountain peaks, no roads or any other power infrastructure. So all this work is conducted together with some local Sami reindeer herders. And what is kind of important to mention at this point is that this network is, because we build it together with them, I mean, this network is actually self-governed network. So, and for these communities, this is actually quite important, because when it comes to, you know, mobile operators coming into this area, they often build their networks as well according to the profit as well, and the considering the costs of maintaining. And it did happen before that, for instance, you know, one of the mobile operators just decided to shut down one of the masts, which left quite a big area uncovered with any kind of a mobile internet connectivity. So I think I'm gonna yeah, on this photo as well, like I can say a couple of words. Like, I mean, you've seen the one of the mobile masts, and we've done this. We took this photo last spring when we were actually going through the terrain and actually clean the this mast from the away from the snow. And what is important to mention as well is that, I mean, despite the strict national park policies, Sami reindeer herders, they have exclusive right to move their herds in the northern part of Sweden and actually use any kind of part of the land as a grazing area. So that's why we're kind of doing this thing up there. There are many conventional products out available to track reindeer herds. However, the problem is that some of them are actually based on mobile network technologies, others are actually even satellite based. But as I mentioned previously, due to the high mountain peaks, you often get into the shade of a, let's say, satellite, or you have a much, or at the same time, you have much shorter battery life, because most of these devices needs much stronger signal to actually send it up to the satellite. Yeah, next. So a few words about LoRa DTN platform. So it's as I mentioned previously, it's tailor-made solution for reindeer herders and this Arctic environment. It is designed to operate in a highly power constrained environment. So basically, the entire system that it's deployed up there, it's actually runs out of solar panel. And this is one of the main reasons why we choose DTN instead of conventional IoT products. And because most of these base stations, when it comes to LoRa, let's say LoRaWAN infrastructure, I mean, they require constant power, which is really not accessible on these mountain peaks, especially not during the harsh winter conditions. So it is worth to say that we have a couple of months basically of Arctic winter where it's impossible to get any solar power. And even if you get it, you will not be able to charge batteries because you cannot charge batteries that are deeply frozen. LoRa DTN is a really lightweight protocol. It's a bit stripped down architecture of DTN, and we use 433 megahertz LoRa radios in order to establish link. And this typically gives us line of sight range, and up in the mountains, in best cases, you get up to 60 kilometers, and in worst cases, you get just maybe a couple of kilometers when there is a thick forest and it's a lot of snow on the branches of the trees. Next. So I'll go through a couple of components of this network that we built. So the most important for any herders is, of course, GPS tracking collar for the reindeer. As you see, this is this photo was taken while we're putting one of the reindeer collar on a reindeer. It is actually possible to put this collar on or off maybe once per year maximum, maybe even every second year. So therefore, the battery life, it's actually quite important to be as long as possible. So in our application, when we actually send signal every half an hour, we get typical lifetime between 1 to 2 years. Next part is actually base stations that actually collect then these signals. And on this middle photo, you actually see one of the mobile base station, which is basically a snow sledge actually attached to the mobile scooter. And these base stations are then getting distributed over the area where they are needed the most, and they can be picked up or actually left over the winter. And on the right, you see actually one of the more permanent masts that we have up there. And as you see, like it's basically consists of a really good and strong antenna and quite large battery. Next. So the next component that it's actually the crucial one is actually a so-called pocket nodes. We call it pocket nodes because users are supposed to carry this with themselves like all the time. And it actually provides the interface between the LoRa DTN network that runs on 433 megahertz LoRa modulation and the actual app that we developed for these purposes. And on the bottom left photo, you actually see a couple of iteration of these pocket nodes. We're still coming up with different designs because one of the key problem is actually the battery life again, because as soon as we enter winter, the battery life goes down from a couple of days to basically a couple of hours when it's used outdoor. So we try to keep these devices warm. And the second part is actually, the second device is called drone node, and sometimes we use this kind of specialized small nodes that are kind of a shape like this. So it's kind of a small thing that you attach under the drone. And it has kind of quite a large dipole antenna. You hang this over the drone, you kind of lift it up in the air, and then you can basically leave the drone up there and until the drone actually, or this drone node collects all the data from the collars around or from the nearest mast. And in the middle, you have a screenshot of the custom-made application for any herders. And previously, although we had this application was used mainly to track their herds. Now we actually added a messaging function. So we have a publish subscribe type of a messaging service that it's kind of it was developed in this year and will be probably, so far we ran some tests, but this is going to be used this winter for the first time for real. And every time when a person actually sends a message, it can actually decide whether to include the position, the location of the message or not, and then send it off. This application it's actually possible to use with or without mobile internet connection. So we have our backup server where all the data eventually is stored. But it is otherwise possible to use it even if your phone lacks any mobile internet connectivity. So next. So this is another screenshot on the right from our app, and you see like this is one of the messages that was sent on a channel called Davadis and from the user Chaco, and then here you see the message itself and the time. And these other icons are actually showing the position of the herds. And you also for all the messages that were sent over this network, actually you can see as well where the user were located when they send them off. In general, the primary use of this network is to track reindeer herd. And quite often it's actually as well used, especially when the reindeer herders needs to work together. They share each other's location with other work colleagues. So as I mentioned previously, you can send short text messages and mark and share various locations on the map. And then being a part of the IPNC community, actually, so it did allow us to, for instance, in theory, to ping individual reindeer, let's say from a space. But I mean, more than that, I think actually being part of the IPNC DTN community, it allows us to kind of follow the DTN protocols and as well assure interoperability with the network that Oscar talked about it before. So for future use, we will most likely involve tourists and maybe hikers that are also present in this area and often lack any kind of internet connectivity. So they should be able to communicate with their loved ones. I mean, for instance, we did implement in this messaging function right now, it is possible to send a message to either a custom, I mean, on a conventional mobile network over the SMS function and to the IPNC network that we're building. So yeah, I mean, it's like one thing that if I kind of return a bit to maybe the previous slide that I actually see that as well, it's regarding the drone node that I kind of maybe forget to mention is that with this setup, it is actually possible. I mean, on average, like if on a relatively flat terrain, we actually do get quite a big coverage. So for instance, with one drone and one pocket node actually lifted up in the air, we were able to actually cover like 30 kilometers range under the drone and establish the links. Of course, this is like in optimal and it really varies according to the terrain. And kind of maybe one thing that is worth to note here as well, it's that we actually had, I mean, first we built this drone was actually built on the drone. We use this DJI drones that actually have the USB connection, and the idea was that we would actually keep the device on the drone. But it turned out that this quite strong video signal that DJI drones are sending constantly are actually causing enough interference to actually completely block the relatively low LoRa signals that we're receiving on 433 megahertz. So it's just maybe one thing to mention. If we return then to next slide. And I think to kind of conclude this is kind of it's kind of worth to mention that this kind of a system is very applicable for any disaster scenarios. And that's actually something that proved already in our application. When, for instance, we have a snowstorm or we have a local mass in these more remote areas gets down, you get quite a large area without any coverage. And it happened that, for instance, when that happened, like I think it was last year once, reindeer herders were actually able to still track the reindeer and see the positions. Unfortunately, during that time, we didn't have messaging servers that they can try, but it is easy to apply and can be quite quickly applied in the various disaster scenarios. This is, I think, shortly from me. And yeah, if people have more technical questions, I would be happy to answer them after this presentation. So thank you.
Okay, now, thank you, Samuel. We're going to hear from Alberto now about the basics of space communications.
Thanks, Ronnie, and good afternoon, everyone, and super excited to be here contributing to this NEXUS talk. So you heard from Oscar about the work we do in the Interplanetary Networking and Special Interest Group, IPNC. And then we heard also from him and Sam about two key applications, two examples, right? How we can manage healthcare in space by having a gateway between, health information systems on Earth and, doctors on Earth and space. And then from Sam, we heard about an application of the delay and disruption tolerant networking for an extreme challenge network use case on Earth. So what I'm going to do is that I'm going to take a step back. I'm going to talk a little bit about the why of DTN, delay and disruption tolerant networking. So I want you to keep those two terms, the delay and disruption, with you for a few minutes, because what I'm going to do is that through a series of examples is to explain, why there is a new type of networking needed compared to, what we have today. So with that, let's go to the next slide. So first of all, if we think about space communications and, more important, data transfer in space, just want to set a couple of terms. The first thing is, when we have a spacecraft, it could be a satellite, a spaceship, a rover that is in the surface of our planet, and Earth, there are typically a few, the type of communication is typically structured in 3 or 4 areas. The first one is what we refer as telemetry. And this is any information that comes from the subject of interest. This could be science data coming from sensors. It could be engineering data about the state of the spacecraft, or, images, videos that are showing us, specific things, both from science purpose or for any other purpose. So that the telemetry is typically what we call as, the downlink. It comes from space to Earth, and this is the, a data that is consumed by scientists, for example. The second type is named as command. These are control functions that are sent from Earth to the spacecraft. So for example, if you have a specific sensor and you want to set a sensor on, or you have a rover and you want the rover to move X number of steps, that's a command sent. Then one thing that is super important, and this has to do with spacecraft that are moving or can move, is tracking and navigation, which is how the spacecraft knows where it is and where to go. And think of it that, space is a 3-dimensional space that is huge and don't have much references to know where it is, as well as for Earth to know where the spacecraft is. So for example, if you have to point an antenna, you need to know where to point it to reach the spacecraft. And the fourth item is related to communications. Now, this is specific to a spacecraft that have a mission or the goal of allowing other elements to communicate. So this could be a relay spacecraft or a communication satellite, in which, in addition to carrying telemetry, command, and tracking navigation for its own operation, it also carries data from other users that goes to other destinations. The reason I'm mentioning this is because if you think about these 4 areas, first, they may have different directions. Telemetry is downlink, command is uplink, is from Earth to space. Tracking and navigation may be 1-way, 2-way, or even 3-way. And communications is typically 2 ways. They also varies in the amount of data, the volume of data. So for example, an image or a video has a large volume of data, versus, for example, command information typically is, the volume is very low, but it's super mission critical, because if you're telling, it's not the same to tell the rover to move 3 steps than moving 3,000 steps. So accuracy of that information is very, very important. So what we're going to see is, through the rest of the presentation, is how data transfer, and starting with communication, is achieved in space. So let's go to the next slide, please. So let me show it with a very extreme example of a space communication. So Voyager 1 is the first ever human-made object, and the one of 2 objects. The other object is the Voyager 2, its twin, that have reached interstellar space. What that means is that these 2 spacecrafts have left the influence of the solar system. So they are very far, far away. They were launched in 1977. So many of us, or many of you, I was born, many of you were not even born yet. And it reached interstellar space in 2012. So it took them a while, to get there. Why am I using this example? Well, just want to give you some ideas of, the dimensions of space. The Voyager 1 is currently about 14.3 billion miles from Earth. That it's moving at 37, almost 38,000 miles per hour, so super fast. And for any message, or let's say for light to get from Earth to the spacecraft, what that means is any message, because radio wave move at speed of light. For any message to go from Earth to the spacecraft, it takes almost a day, takes more than 21 hours. What that means is that if you send a message to the spacecraft and you're expecting a response, you have to wait for 2 days for a response, okay? Then if we look at communications, just a couple of characteristics, they communicate via microwave links, in this case, an X-band, a gigahertz link. And the signal level that is received on Earth is very, very, very low. It's 110 at minus 16 watt. In order for it to communicate, typically, or the only way to communicate with those spacecraft is via the NASA Deep Space Network. So that's a series of large antennas we're going to talk about a bit later. And the most interesting thing is that the current bit rate, it's 160 bit per second. So that's the maximum data transfer speed that is achieved today. And that's due to primarily the long distance. So just compare that 160 bit per second with what many of us get at home, anything from 200 megabit per second to gigabit per second. So we're talking about, more than a million times, or, more than a billion times, I would say, the speed that we have on, we at home, we receive more than a billion times the speed that this spacecraft have. But this information is super important because this is the only way to get an understanding of the universe and the solar system. So these 160 bits per second are extremely valuable for us as humanity. So next slide, please. So I basically mentioned before for you to keep in mind 2 terms, distance and disruption. So I'm going to talk about distance and the effect of distance in space communications. So if we think about typical distances in space, and I'm going to use three areas. The first one is anything that is close to Earth, let's say from Earth to the moon. We're talking about hundreds of miles. That's basically the low Earth orbit where the International Space Station is, to hundreds of thousands of miles. So for example, the moon, who is, I think is about 250,000 miles from Earth. That's, anything that is close to it. So for us to communicate, any communication that is done within that area would take from milliseconds to seconds of delay, or latency. What that means is that, for example, if you say hello, the other person would hear it certain milliseconds to certain seconds later. And as an example, anything that is beyond 500 milliseconds constitute a very big barrier for having a traditional telephone call, real-time interaction. And then you have certain signal loss if you're using radio or optical communications. Then the next step, if you think about, okay, how about communicating within the solar system? And within the solar systems, you're typically talking about hundreds of millions of miles. Now the communication delays become much larger. From seconds, now we're talking about minutes to hours. As an example, the delay between Earth and Mars varies between 3 to, I think it's 25, 27 minutes, depending on the relative position of each other. So if I say hello, the other person won't hear it until 3 to 25 minutes later. If I'm waiting for a response back, I have to wait from 6 minutes to an hour to basically hear back the, hello, I'm doing well. Then the signal loss is much higher or much bigger because, the object is farther. And now if you think about interstellar space, which is the case of the Voyager, we're talking about communication delays that are in days to years. And the signal loss is much, much higher as well. So if you think about distance, it impacts the communication delay and it impacts the signal loss. And what that means is that the following: with communication delays, we cannot do anything other than waiting. Radio waves and optical waves, they travel at the speed of light. And, at least until now, we haven't found a way to overcome that limitation. we would never know if that, I mean, we don't know yet if that is possible at all. This is, a hardcore physics. So the only thing we can do is adapt the communication style. So for example, if you cannot have a telephone call because the delays are too long, you rely on messaging, which is you record your voice, you send your voice, and then, when the other person receives it, record it and send it back to you. The second thing is the signal loss, and this has to do with, hey, how do we ensure that we can have enough signal so we can decode the data? Well, that has to do with putting money on the table. Larger antennas, better amplifiers, better receivers. What that means is that the communication network becomes much, much costly. I mean, it's, space or deep space communications these days are extremely costly because each of these antennas cost, hundreds of millions of dollars and then tens of millions of dollars to maintain it every year. Next slide, please. Then the second piece that is super important is disruption, and that has to do with celestial mechanics. Planets and natural satellites rotate. They move around an orbit, and depending on that, depending on the time of the day, depending on the day of the year, they are in different relative positions. As an example, we just came out, well, I say we, but yeah, Earth came out of a solar conjunction with Mars, which is a period of 2 weeks in which pretty much the sun is in the middle, in between Earth and Mars, and communication is not possible, or reliable communications are not possible. So that's another extreme example of disruptions. However, disruptions happen every day. Earth is rotating. If you have low Earth orbit satellites, you may have an orbit that you may be in a situation where you can only see the satellite during a window of 3 to 4 minutes and in passes of 90 minutes. So what that creates is disruption. You don't have a continuous line of sight between the two elements. How do you solve that? Well, you solve that by incrementing the coverage. On Earth, you have to distribute antennas 120 degrees apart, so that at every point of time as Earth is rotating, there is one antenna that can cover that communication link. And then from space, what you do is, depending on the orbit, you have your spacecraft on Earth or on a different planet or natural satellite. It's by adding satellites. So if you are in geostationary orbit, you can cover the planet with 3 satellites. If you are in medium Earth orbit or low Earth orbit, then you need to multiply that number by X. So for example, for medium Earth orbit, you may have a decent coverage with 10 satellites. If you go to Leo, you may need 50 satellites, and I'm just talking about the equator. Then if you're in a situation as Samu was explaining, where you are in one of the poles, then it's a completely different situation or completely different nightmare. So disruption affects, again, the way 2 elements in a space can communicate, because everything is in a space is moving unless you are in a Lagrange point. Next slide, please. And then the last thing is related to the spacecraft constraints, which is, you are going to put a spacecraft, well, you need to send it from Earth, and there is something called a space velocity, which is the velocity you need to achieve, or the spacecraft needs to achieve to escape Earth gravity. And because of that, you need to put a lot of powerful rockets, fill it with a fuel, and how much fuel, how many rockets, it all depends on what you're carrying, how heavy it is. So because of that, there are huge constraints in swap in size, weight, and power. It has to be, anything that you do for space has to be as small as possible or concise as possible, because it needs to fit on the transport or on the spacecraft. For example, if we go to the ISS, in communication, this affects things such as the antenna size. The antenna, because you need to transport antenna, it has to be a certain size, and there is a direct relationship, at least for microwaves, direct relationship between size and gain. Then for weight, it has to be low weight, because more weight, more fuel, more expensive. And for power, it has to be super efficient, because you want the mission or the lifetime of the spacecraft to be as long as possible. So you need to be to make communications very, very efficient. Next slide, please. And then what the way we, and when I say we, is the scientific community solve this problem is by segmenting the space networks, so that you find kind of certain common elements in each of the areas. So on Earth vicinity, first you have the typical orbits. You have the low Earth orbit. So for example, the International Space Station is there, a lot of satellites. Starlink from SpaceX is a network of satellites in the low Earth orbit. Then you have the medium Earth orbit. There are satellites there primarily for communications, and then the geostationary orbit. Geostationary orbit is the only orbit in which satellites are kind of static from any point of Earth view. And that's because they are geosynchronous with Earth, which is basically they move at the same speed as Earth rotates. So GPS are in geostationary orbit, and then a lot of communication satellites or NASA TDRS are in geostationary orbit. And then you go all the way to the moon, and that's what NASA considers as the near space network. It's a network that covers Earth vicinity all the way to the moon. Then anything outside that becomes the deep space network. So if you think about, coming back to delays, if you think about delays, anything that goes to the moon, it's in the order of seconds. So the delay between Earth and moon in light speed is around 1.3 seconds. So the traditional internet protocols kind of work. They don't work out of the box, but they can be optimized to kind of work in terms of delay. However, if you add disruption, so for example, you want to communicate with a telescope that is on the dark side of the moon, then TCP/IP becomes a problem. And this is where delay and disruption tolerant networking has a big role. And the main protocol for DTN is the bundled protocol. Next slide, please. Quick example, 3 seconds. This is NASA Near Space Network. It's comprises a bunch of ground station in different part of the world. They are now adding more stations on the poles to have polar coverage as well. And then on the boxes is a series of geostationary satellites that provide relay services. These are the TDRS satellites as well. They have 8 satellites in operation. So this is how you achieve 24/7 communication, for example, with the International Space Station. Next slide, please. And then for deep space, which is communicating with Mars and beyond, there is a series of deep space antennas. And as I said before, how do you achieve global coverage? 120 degrees separation. So there is a network in California and Goldstone, one in Madrid and one in Canberra. And these are huge antennas, 34-meter antennas, 70-meter antennas. I'm talking about the diameter of the antenna. So these are huge, huge monsters. Next slide. And I think this is my last slide, which is when we talk about the interplanetary internet, it's also referred as the solar system internet. The goal is to provide a communication network for data transfer and data communications that covers the Earth vicinity, covers the moon, covers Mars, and then asteroids. And then, we'll continue growing from there. So this is a huge endeavor. We estimate that it will take us and whoever comes after us around 100 years to build this network. With that being said, Ronnie, all yours.
Okay, thank you, Alberto. So yeah, take a look at this picture that Alberto has up here and the complexity of connecting all these entities, right? And that's kind of what we're looking at helping from here at Utica College. So you guys know enough about me. I don't have to do anything there. Here's our support infrastructure. So this is what we've been building. I've been kind of working on this for the past couple of years. I've been heavily involved with the IETF's delay tolerant networking and MANET working groups. I've also been doing some stuff over the AFRL with research, and I've came across this eMain platform, which I've been using to build clusters to emulate different things like drones and interactions between them, as well as now we're using this in the Interplanetary Internet Prototype Network to emulate clusters of satellites or other entities that we're trying to communicate with. So here's the picture of the server rack we have in the college data center. Over here, we can see the IPNC PWG, which is the Solar System Internet Prototype. And each one of us that have spoken today have nodes sitting on that prototype network. And we use that during our bi-weekly meetings to do testing and communicate between each other and test these protocols that you've heard a little bit about today. So we have this node Helios, which is sitting out here on the end of the network, and it's acting as a gateway on our it's got its own public IP address. It's sitting in the computer science network. And it's sitting here as EIN number 42 on the Interplanetary Internet Prototype Network. What I did here is I allowed it to come into a Cisco switch in the network. So this is dual homed. It's got a network card on the WAN side, connecting out here to the world, and a network card on the LAN side, which makes it act as a router. So inside, I have a physical switch with multiple machines behind it. One of them is acting as a data storage server, home directories. We're also going to be doing system monitoring, stuff like that from this system here. Here we see the eMain cluster. It's a high performance computing cluster. And each of these nodes is capable of launching up a 200 or so virtual machines that I can do a whole bunch of crazy networking testing on these in situations that allows to really expand out this testing platform and run different applications on each of these very lightweight virtual machines. I don't want to say next slide because I control the slides. So a little information about this test bed. We're using these 1U rack mount Supermicro servers. They're about circa 2012. They are approaching their end of life, but we're still getting what we need out of them at this day. We're running a Ubuntu server on them. I talked a little bit about the gateway node here and these ERMIS, which is that network monitoring node and shared NFS storage. And then we also have the cluster, which again provides hundreds of virtual nodes behind node 42. So this allows us to extend our network. They see node 42 from the IPN. They come in, now we have this whole blanket of testbed of network. We can build an internet behind here of different routers, different segments, different regions. So the nice thing about that as well is it allows us to bridge all these nodes back to that physical network from the way I have it configured. So say I run up 1,000 nodes behind this network on 4 or 5 different servers, all those can come back into the physical network and then be relayed back out that node 42 to be communicating out on the IPN or send messages and receive messages from there. We can arrange them in clusters or regions where they would all have their own individual subnets, simulating what we have today as an internet on Earth, right? Where we actually have companies have their own routers, schools have their own routers, and behind them they have hundreds, maybe thousands of machines that are all communicating out from that single endpoint. And that's what we're trying to simulate here to actually provide this large testing bed for the IPN. We have the ability to add latency, jitter, delay to these certain network segments, make them just completely disappear, come back again as if they were simulating satellite communications. And we can assign multiple network cards to each virtual node, so we can start creating mesh networks depending on what kind of type of topology we're going to need to work with. All this is actually controlled through automation, and I'm setting up with this Python ETCE control framework, which is open source and developed by the people who develop eMain. It is Python 3 based, and a lot of our students are very versed in Python at Utica College because that's one of our introductory programming courses. So this is very easy for them to get a hold of as we start working with them on this. We can automate node configurations, network setup, and topology. And if you think about this in terms of trying to launch 1,000 nodes and configure them all to do individual little things, send out data, receive data, communicate, move around as if they were moving in 3D space, right? So we got positioning and telemetry. We can spoof and send them that information. So we can really create this grand simulation and then do a lot of different things to really support the building of this network. So this semester, we're running the CSC 300 special topics course called the Interplanetary Internet Prototype Network. Next semester, we're running it again as the Solar System and Prototype Network. So students are actively participating in IPNC PWG working group meetings, and they're acting as the scribes. They're taking notes for us. They're relaying back to the chair. So we have that active history going on, and we're preserving that as we have these meetings. And these meetings happen twice a month, or every other week, basically. They're also participating in the testing plan and helping to evolve that testing plan and really testing out a lot of the bugs. And we're working with Oscar and his team on that extensively. They're developing documentation for that. So one of the projects they've been doing is Up until this point, we're at midterm. We've been working with ION DTN, which is the NASA implementation of the bundle protocol. And they've been learning a lot of the idiosyncrasies of ION, how to use it, how to set it up, how to get a system up and running, how to actually send communications between them. And they've been using the laptops from their home internet connections and actually testing as if they were out in space, communicating with each other. So they're getting a good handle on ION and the utilities involved in ION, and they're using those to provide documentation and build a grand documentation scheme that we can provide back to the IPN-SIG so that end users like yourselves can join the testing plan and follow the documentation from bare metal machine to getting up and running with the testing plan that we'll talk about in a little bit, the software, and have an ION and everything configured and ready to go to actually be a contributor to the testing plan and the information gathering we're doing there. The second half of the semester, we're going to start working with the micro DTN, which is from Germany, and we're going to start getting them involved in learning the same process we did with the ION, documenting the whole procedure, getting that set up, and then we have to start looking at the interoperability, right, between these two different bundle protocol implementations. That's a little bit about what Alberto and Oscar were talking about before. So how do we start providing interoperability between all these different implementations of bundle protocol from all over the world? And that's where we're going to start going down. We're starting with these two, start implementing them out on our simulation platform, and then start, as time goes on, bringing in more and more bundle protocol implementations and continuing to test them out and start trying to build an interoperability mechanism to start having all these talk together. So the ION DTN testing plan, it is a complete system. We have registration forms available, downloadable software, installation manuals, user manuals, support forms. We have a volunteer support personnel system, which Oscar has been managing, feedback for results to users, as well as statistics publication. So Oscar has created a very large database to gather all this information and produce meaningful information and data back to the community so we can see how this is actually progressing. So you can register yourself at the IPNC pwgblogspot.com, the testing plan. If you want to go there, there's a lot more information to actually become an active participant in this. And we encourage you guys to do that. There's an email down there to get more information and support from the group as well. So with that, we want to thank you very much from all of us at the Pilot Projects Working Group. I'm going to hand it back to Oscar to kind of wrap up anything, and then we'll take any questions. Thank you again, guys, for speaking today.
Thank you very much, Ronnie, for Alberto, Samo, for outstanding presentations. I am sure there are some questions in the chat. Before I start answering, I would like to comment in this in my closing of this, that we have from the two universities and technical colleges. We have Dr. Ali Abedi that kindly accepted my invite from the University of Maine. I don't know if Ali is already around, and you can say hello if you wish. I don't know if you are still there. And we have Eunice Perez Coelho from the Technical Institute of Merida in Mexico, in the Yucatan Peninsula. So they are very kind, and I think they are very interested in our talk. So well, and I would like to thank the Utica College that has been really kind in giving this space, the Nexus Talks, to make this presentation to all of you, that I hope it has not been boring and you have been interested. Well, thank you, really thank you to all on behalf of IPNC and the Pilot Project Working Group and all the speakers. We are open to questions. I guess Elizabeth has some questions there from the chat. If you would like, Elizabeth.
Yes, Michael, you're free to unmute yourself if you'd like to ask it. If not, I will ask it on your behalf. Okay, go ahead.
Oh, please speak. I might be.
Okay. Sure. So Michael is asking about what is the most practical coordinating system for pointing antennas from the Earth to the Moon, from the Earth to planets? Time coordinate is also an issue.
Yeah, so a couple of things. The first one is, let me start with timing, because that's the main, in order of magnitude, that's the most important piece. So the way timing is achieved is twofold. Either you have a super accurate clock, and let's say an atomic clock for that instance, or you derive time from a well-referenced clock that is somewhere else. So on Earth, typically, ground stations and the systems have atomic clocks because, size, weight, and power is not an issue. So you have very accurate atomic clocks, and they typically become the timing reference for the spacecraft. So on the spacecraft, because of the constraints, at least till now, you don't have that level of accurate clocks. So the way you get timing is through the radio signal. So the radio signal itself has a very specific carrier frequency, and by the magic of electromagnetic theory and the Doppler effect, you are able to understand time difference between the origin and where you are just by decoding the signal and looking at the Doppler effect. The Doppler effect also, very interesting, tells the spacecraft where it is and how fast it's moving. So just by looking at the signal itself without any other reference, you get a good idea of where the spacecraft is, and then the spacecraft can send that information back to Earth. So that's the way Earth knows where the spacecraft is. So this is like a two-way tracking that is performed. Now, when it comes to the specific coordinates, the answer depends, but typically, we're talking about spherical coordinates, and you have coordinates that are more planet-centric, or it's called planetocentric, in which for example, from Earth out. So anything is represented from Earth, latitude, longitude. And then there are others that are more relative, like SPICE coordinates, and then this is more related with the two elements in a space move. These are just the basics. There are much more ways to measure things, and I'm definitely not an expert on tracking and navigation, but that's basically what I can add.
Thank you.
There is another question that I guess Alberto is most proficient in this. Will any space relay platforms we use will platform is Lagrange points to be used? The question is about relay platform and the position of the platform in terms of the Lagrange points.
Yeah. So a couple of let me separate those two, and thanks for the question. First is relays. Relays are typically, when we talk about relays in space, these are spacecraft, satellites that think of it as repeaters. So they take the information from one spacecraft and repeat it, relay it back to Earth or back to the planet where the other spacecraft is. And there are quite a few out there. So the most, I think the most sophisticated ones are the tracking and data relay satellites, TDRES. These are in geostationary orbit right now. And for example, these are the ones that allow the International Space Station to communicate to Earth 24/7. And the reason I'm saying this is because keep in mind that the International Space Station, irrespective of how big it is, it moves, it basically rotates around Earth every 90 minutes because it is in low Earth orbit, so it's not geostationary. So there is not a single reference point. So the way to have a single reference point is by using a relay that is in a reference point, and this is TDRES. There are also other relays in Mars, for example, and in the Mars Odyssey mission was repurposed to be a relay. But for example, the Mars Odyssey mission satellite or satellites are not in Mars geostationary orbit. So the fact that you are a relay doesn't mean that you are in a Lagrange point. Definitely there are plans both for the moon and for Earth to, well, for Earth, definitely the geostationary satellites are in a Lagrange point, but for the moon and for Mars, to have elements in the Lagrange points. The problem with the Lagrange points is that they are typically far from the surface. And if, as you know, the farther they are, the more expensive the communication equipment is, because you need to have more power to transmit the signal.
I would like to add also about this relay thing, this relay question, that one of the topics that one of our board members, Vin Surface, is always talking is about sending a probe or some kind of spacecraft to Alpha Centauri. So one of the reasons also to have a solar system internet is when you have such a distance, and we have had some seminars about communication with laser beams, when you have such a distance, the situation is that the spread of the signal that you get is very wide and ample. So to get that, you need relays in several points, and this is millions of miles or kilometers. So this would need to be a network that is spread on the dispersed on all the solar system to get that information. I don't know if that helps a bit more or makes the problem more complicated.
If I can add, I think I remember when we discussed deep space network once with one of the scientists, I forgot who are measuring. I mean, they have one of the probes in a space, and he said that on average it takes 2 to 3 weeks of planning of entire team to actually make a schedule to download the data from one of these probes. So it's quite a big challenge, and I guess this interplanetary network, I mean, one of the goals is to kind of simplify this process as well.
So if I'm understanding from the beginning of the presentation, the IPNC uses a lot of available resources, which I imagine requires a lot of networking, like in the people sense and the non-technical sense. So how do you start those conversations with all of these organizations and governments and individuals, and how are you making this all work?
Well, I am going to give. We keep. Well, there. This is a very important and interesting question because what happens is that in a certain point, as I said on one of my first slides, this is an endeavor for many. For most persons and for governments, because it also gives an important hope. I guess that I say, and I wrote that in a newsletter some time ago, that this this pandemic that is not that is decaying but is not gone, has also prepared us to be astronauts, because we are used to live in secluded situations. We weren't 2 years ago or 3 years ago. We were used to that. We were not used to that. We're used to communicate on the internet or virtually. And so it's quite a training. It's quite a training. So what happens related to your question, that when we start conversations, we see that these big organizations, governments, space agencies, companies are open to talk about this. And they have been thinking on this same track, perhaps with their different resources or ways. So it's quite a job, because we have meetings and we talk with one and the other and all that. But it's an interesting point that when we launched this solar system internet project, that if you would have done something like this 5 years ago, everybody would have said, well, this is crazy. Well, no. We have a very good reception. And of course, it's not easy. Yes, but it's very, very interesting and very, we have a good hope in this moving forward, Elizabeth. Thank you for that question.
Some of us are also on other things like the IETF and different working groups there where we have other connections that spider out. We brought a few of those people into our meetings as well. So, you know, it's just really, like Oscar said, building out that spider web of just different connections from all the different space agencies and trying to get them involved in our mission as well. So there is a lot to it.
And I will also add that, for example, a conversation like this in Utica College, in the NEXUS talk, that has arised an important interest, was not so easy some time ago. So I think that that this shows a global decision and interest of people to get involved in this.
Well, I'm not seeing any more questions in the chat. So on behalf of Leonora and myself and Utica College, I just want to thank you so very much for being here. It was truly wonderful to meet you all virtually and hear this presentation. And yes, I think you're right. You have sparked some interest, and I hope that exciting things come out of that. And please remember to visit the links that Ronnie posted in the chat, and which are available on the screen, and share your ideas with this group. So thank you very much.
Thank you. Thank you. Very much appreciated.
Ended with hope. That was good. Ending in hope. It's nice.
Thank you, Leonard. Thank you, Elizabeth, for your great job and your support for us. Thank you very much.
Wonderful. Thank you.
Thank you all.
Thank you everybody for speaking, and thank you for everybody for hosting and the students for participating, and it's just a great thing.
Goodbye.